Christoph already mentioned, I'm going to present the g.tec suite, and I already reassembled the cap on my head because it's going to be a live demo. I'm going to build some signal processing chains that can acquire and process EEG in real time to get band power features and an P300 experiment that I'm going to show you in this talk. The g.tec suite 2024 is software suite for all the research and clinical amplifiers. You can see the software suite looks like this. You have math tools in there, you have applications and development tools in there. You also have a licensing section because some of the tools require license keys to be unlocked, or some features are locked with license keys. Then you have an update section, so we always test and ensure that all the software delivered is compatible with each other, and all the software is delivered with the updating tool within the suite 2024. And in case something goes wrong, we also have a diagnosis tool, so we can check your hardware and software environment to find bugs easily. For the applications, we have the g.tec test. This is a functional electrical simulator for muscles. We have the g.tec Pro, which is also a simulator, but in this case to simulate the brain invasively. And to stimulate with electrode grids in the brain, we can also use the switching unit. So these tools are more used in the clinical environment and requires more surgeons and research medical environment. So we're not going to show them today. But I'm going to show G-Recorder later on, which is a software to record and visualize EEG data in real time. We also have montage creator, because if you're using caps and grids and different electrodes, it's sometimes important to know exactly where each electrode is located, and therefore we have these montage creators. For the Unicorn PCI core, we have the Unicorn PCI core recorder, which is also showing EEG data. It's visualizing EEG. You can record EEG and you can stream it via network. And we have some tools that require MATLAB runtime, the converter to convert our file format to other file formats like EDF, for instance. We have GBS Analyze, which is our offline processing framework. That's also one tool that I'm going to show later on. And I'm going to show g.tec, which is a prototyping framework for signal processing chains. It's a drag and drop editor where you can create signal processing chains. And I'm going to show you how to extract band power features and stream it to some external application and some ERP features later on. I'm also going to show how to load data recorded with g.tec in GBS Analyze. And we also have some development tools. So if you don't want to use the software we provide, we also have APIs for raw data access for different programming languages. One commonly used programming language is C or C#, Python, MATLAB, and we also have a network API if you want to implement it in any other programming language. And then we have APIs for the StimBox and g.tec Pro switching unit. This is the whole toolset for research and medical applications. And some of these tools are locked with license keys, so they cannot be used without the license key. And some features can be unlocked with license keys. So to give you an overview, the locked or unlocked features are listed in here. So the g.tec suite itself requires a license key, so you cannot download the update and install it without the valid g.tec suite 2024 license. And we have g.recorder, which can display data if you don't have any license. If you have the basic license, you can record data. And if you have the professional license, you can use all of the features like ERPs and other features that are included in the professional license. Devices cannot be used without any license. With the basic license, you have a limited block set, and with the professional license, you can use all the available blocks. GPS Analyze also requires a license. If you unlocked it, you can use all of the functions. And Unicorn BCI Core Recorder uses the same license as the g.tec suite 2020. So if you buy the g.tec suite 2020, you will have Unicorn BCI Core Recorder as well. This is the license dialog, so you can insert your license information and then unlock software modules within g.tec suite directly. And in case something goes wrong, we also have the diagnosis tool, your Windows, your MATLAB environment, all the version numbers for the required software modules, so we can find bugs easily. And as mentioned before, this session is a hands-on session again, where I'm going to, where I've prepared some demos. So I'm going to present HYSYS first. And in HYSYS, I want to show you how to establish some real-time data acquisition and display. And then I want to extend this model further and further. First of all, I'd like to add some signal processing, and I'd like to add data storage, and I'd like to extract some features, in this case, band power features. And then I'd like to show you how to stream the data from HYSYS to some external application. I also want to show you GBS Analyze. In the HYSYS model, we are going to add some data storage, and I'd like to show you how to load this data in GBS Analyze afterwards. And finally, I want to show you g.recorder, which is another standalone application. And I want to show you how you can stream data from g.recorder into g.HYSYS. That's usually used when g.recorder is used in a medical or research environment and is recording some patient data. But you also want to run an experiment in parallel, then you can record and run the BCI with g.recorder, but in parallel, you can do some research signal processing in g.HYSYS. And therefore, I'm going to show you how remote data acquisition works using these tools. Okay, I've already opened MATLAB. And first thing I'd like to do is create a new model. We're going to build this demo from scratch. So I need model output test. And first thing I'd like to do, set up the model in order to be able to use the Nautilus that I've already set up on my head. And therefore, not just loading still a bit. So I have to wait for some. Already set up the model settings. The Nautilus that I've set up right now will be recording with a sampling rate of 250 Hertz. For I set the model to a fixed time rate of 250 Hertz. This is important for setting up filters correctly, because they have to know frame rate of the device. And then I'm going to add some blocks, and the blocks are within the g.tec library. And first of all, I'd like to add an amplifier to the model. In this case, I want to configure it for the Nautilus. And after adding the amplifier, I also want to see data. Therefore, I'm going to add some scope for visualization. The block on the left-hand side is acquiring data, the block on the right-hand side is visualizing data. And in HYSYS, which is a node editor, it's very easy to type signal processing pipeline, which connect the nodes to each other. So right now, I'm visualizing whatever data is transmitted from the block on the left-hand side to the right-hand side. And first of all, I have to configure the device myself. And I can already discover an Nautilus device. The first thing I'm going to do is configuring the device for the experiment. Therefore, I have a lot of options. I have an 8-channel device set up. I'm going to set the input range to plus minus 2250 millivolts. So we're for sure not losing data there. And I'm going to set the high filter only so we can remove the DC offset and see some DC corrected signals. That's all I'm going to set up for now. And that's it basically for the first task that I've defined, creating a real-time data acquisition and display. It's very simple. It just took a couple of minutes. And now you should already be seeing, data floating in. So we can already see data floating in. We still have offset, so I stop talking quickly. And we can already see the data is still very noisy and it's not looking very clean. For I have to add some signal processing. First of all, for the preconditioning of the signal, and we can do this with simple filters. So in the g.tec library, we have some pre-processing section, and in here we have all kinds of filters. And for this experiment, I'm just using surface EG. I'd like to add a bandpass filter and a cascading notch filter. Cascading notch filter removes the power line hum, and the bandpass filter is limiting our frequency range. First of all, I'm going to add the cascading notch filter, and then we can check the impact of this filter again. I'm going to configure it to second order, 250 Hertz, and maximum cascading frequency of 100 Hertz. And now I can run the model again, and we should already see some more clean EEG because the power line hum will be removed. So EEG is already looking better. The cascading notch filter removes the power line hum, but still on the bottom channels, you can see a lot of noise. So I want to limit the bandwidth that we use for our signal processing again. And therefore, I'm going to add a bandpass filter. The next step is to configure the bandpass filter. For surface EG, most of the surface EG is located within a frequency range of 0.5 to 30 Hertz. You can also go up to 50 Hertz, but most of the signal is within 0.5 to 30. And we have a sampling frequency of 250 Hertz. Inserting the node. On the left-hand side, again, just a node for propagating EG data. And we go through the bandpass filter and removing DC offset and limiting it to a range of 0.5 to 30 Hertz. And we remove the power line hum using the cascading notch filter. And then I'm displaying data. So now we should see clean EG, and we can make some simple signal quality tests to see if we're really looking at EG right now. The model is running again. You can see that all of the channels look similar and not too noisy. And now I'm going to make some simple tests. I'm going to blink my eyes a couple of times, and we should see that especially on the first couple of channels where the eyes are located. So you can see the eye blinks on the first channel. So I'm going to blink 3 times again. So you can see 3 times the EOG artifact. Now I'm going to clench my teeth a couple of times. Now I'm clenching and holding. And now you can see some high frequency and high amplitude artifacts due to muscle activity from the genes. These are considered as EMP artifacts. Now we've just seen baseline EEG and some artifacts. The only EEG signal that I can actually trigger by will is closing my eyes and getting some alpha activity. And therefore, I'm closing my eyes for about 10 seconds now. And you should see some low frequency but high amplitude oscillations, which are actually EEG signals. They are alpha activity. I'm closing my eyes now. You can see some very nice alpha oscillations in here. They come and disappear from time to time, and that's typical for alpha activity. All right. Now we've done the first 2 sections. We've acquired EEG and displayed it. We added some signal processing for preconditioning EEG, and now I'm going to add some data storage. So we can also analyze data offline afterwards. And therefore, again, I go into the g.tec library, and I'm going to data stream, and I'm going to add the node save data stream. So usually when you're doing research experiments, you want to acquire raw data, and therefore I'm connecting the data stream directly to the output of the amplifier. So we are acquiring raw data. I rename file to data. That should be sufficient for the test. And now I can run the experiment again. We're still able to visualize EEG. Now we should also see EEG being recorded in parallel, and there should be a file being created that is called data. And we can already see file is here, called data, and that's a timestamp. And later on, we're going to load the file in PBS Analyze. All right, now we have real-time signal processing, display, and data storage. And now I'd like to show you how you actually extract a feature from a power feature in this case. So when I'm closing my eyes, I can trigger alpha. And that's one of the features that I'd like to extract. And alpha is a signal of relaxation, and beta activity is a signal of stress or mental activity. So I'd like to calculate a ratio between alpha and beta, and I'd like to show you how you do that in devices. So first thing I'd like to do, I'd probably like to remove some channels later on and just look at the visual cortex. So therefore, I'm going to add a node for selecting channels. First of all, I will enable all of the channels, and later on we can remove some channels and look at the impact onto the band power feature that we are selecting. So I have a device with 8 channels, and therefore I set 8 channels and add all of the channels to g.tec position for now. And the next thing I'd like to do is to calculate the band power feature, and you can find the node in the feature extraction. And here we can find the node for band power extraction. With this node, we can quantify the alpha activity a bit better, and that's why I'm going to add it in here. I have a sampling rate of 250 Hertz. Alpha activity is usually in between 8 to 12 Hertz, so this should be fine. And I'm going to increase the window length a little bit. That makes it a little bit more stable. 500 samples should be equal to 2 seconds now. So if I'm closing my eyes afterwards for 2 seconds, we should see alpha increasing. And I'm also going to add a second node, which is identical for beta activity. So I rename this one to alpha, and I rename the second node to beta. So again, in Simulink, I can simply connect the nodes with this drag and drop editor. So we're getting data from the acquisition node, from the amplifier node on the left-hand side. Then we're selecting the 8 channels of the device. And then we're forwarding the EEG and calculating band power in here. So I can merge these two outputs now. So we should have 8 channels for alpha activity and 8 channels for beta activity now. And I want to see all of the channels in the scope for the next step. Merging the two signals into one, and I'm going to add a scope. So now, whenever I'm closing my eyes, the levels of the first 8 channels should change, while the level of the other 8 channels should remain similar. So I'm going to test that again. I'm starting the model. On the first scope, we can see the raw data again, or the filtered data. And actually, I've connected the band power estimation to the wrong nodes because we don't want to, I want to add that to the not filtered signal, because otherwise band power will be falsified a bit. I'm running the model again. Now we should see alpha and beta activity. And whenever I'm closing my eyes, the values should change. So on the top left, you can see the raw data, the filtered data coming in again. And on the right-hand side, we can see alpha and beta activity. Let's scale them to similar ranges. And when I'm clenching my teeth, I can induce high beta power. So you can see the value increases. And if I'm closing my eyes, you should see alpha activity. You can also see that there's a change. But it's a bit hard to follow these traces, and therefore I will try to calculate the ratio in between alpha and beta so we can follow the experiment a little bit easier. And that's what I'm going to do in the next step. We have 8 channels of alpha band power and 8 channels of beta band power. And to calculate the alpha beta ratio, I'm going to calculate alpha divided by alpha plus beta. Then the ratio should be within a value of 0 to 1, and it's a little bit easier for us to follow. So that's how I do it. The first node is summing up the alpha and beta channels. And the second node is dividing alpha divided by alpha plus beta. And probably 8 traces are still a little hard to follow, and therefore I'm also going to add a mean. So then we should have one channel with a band power feature, and it should be easy to check the results there. So again, I'm going to add a scope so we can also visualize data. I add a third scope. First scope on the top is for filtered data. Second one is for alpha beta ratio, and the third one is for 8 channels of alpha and 8 channels of beta, and we can check the different results in real time. The model is up and running. And we can just follow the third path. I'm going to scale it to from 0 to 1 because now we will get a ratio in between 0 and 1. And I've checked the displays again shortly, the dimensions of the signal. All right. So looks good. It's like I've misconfigured the one node. Try it again. It's like I still have a mistake in the last section. Then I'm going to work with the other part. You can still see as soon as I close my eyes and clench my teeth, the power values are changing. So now clenching my teeth will change the power signals on the left-hand side. And closing my eyes will change the band power values. Yeah, so you see a rise in the first 8 channels. This is alpha activity. And on the bottom, you can see an even higher rise when I'm clenching my teeth. This beta activity. And on the signal quality scope, you can still see it in the time series. I'm clenching my teeth, like this, closing my eyes. Looks like this. And the next step I'm going to add is to add a lab streaming layout, so you can prototype your signal processing within the HYSYS, and then you can stream out to an external application. And therefore, we have a LSL node in the HYSYS library. So again, go to the library and to network or lab streaming layer, exactly. Then I'm going to add an LSL send node. And I'm going to use the 16 channels of power values that we're calculating and sending it via LSL. So I name it to HYSYS out. And we're sending with a sampling rate of 250 Hertz. All right, and this is the final part for the feature extraction demo. And we have the real-time signal processing, display, data storage, the feature extraction, and the streaming. If I'm running this example now, we can again check all the scopes. And in parallel, I can also stream data out and test to receive it with streaming layer. So again, we can see the EEG. Linking is still there, clenching is still there, and alpha is still there. We can see the 16 channels of alpha and beta features. So when I'm closing my eyes here, you can also see a change, especially in the first 8 channels, because that's the alpha activity. And we're recording this data and streaming it in parallel. And now I try to receive this with a lab streaming layer demo application. So if you would create your own application, you can attach to the left streaming layer stream and put your application based on that. And in here, we now receive 16 channel with 10 power features calculated in HYSYS in real time. You can build your application based on this. You can prototype the signal processing in the HYSYS, and as you have seen, in less than 30 minutes, we established everything from recording to streaming, and in parallel we did all the signal processing and prototyping. And that's why this library is very useful for developing signal processing chains and prototyping. Oh, and now I see the mistake that I've done. I just forgot to change the frequency range for beta. That's why we saw identical values for alpha and beta. Now this third scope should be working as well. Let me mean again. Model is up and running again. So on the top left, we can see raw data. On the bottom left, we can see 16 channels of 8 channels alpha activity, 8 channels of beta activity, and now we can see the ratio in between 0 and 1 on the left-hand side. I'll scale it to the correct range, so we can see that as well. And I've averaged all of the channels that I have right now. So if I'm clenching my teeth, the value will go down. So you can see it dropped a bit. And if I'm closing my eyes, the value will rise. So now we have calculated alpha beta ratio and prototyped the whole signal processing pipeline within 30 minutes. So this was the first example. And now I want to show you how to process the data that we've recorded in TBS Analyze. TBS Analyze is an offline processing framework. You can import data from amplifiers, from g.tec amplifiers. You can record with g.tec. You can also record with g.recorder. I will take the longest file that we have recorded now and will import it. And then you can do some processing. As mentioned before, I've recorded raw data with a high filter. And now I want to process the data for fault surface EP. And therefore, I will add some filter. The first filter we want to add is the notch filter again. So I'm going to add a cascaded notch filter for a frequency range of 50 Hertz. The power line comes in Europe. I want to apply this filter for all 8 channels. Now you can see signal changed a bit and we're removing power line harm. Then I want to add another filter for default surface EG. And therefore I'm creating a new filter. I'm creating a Butterworth filter from 0.5 to 30 Hertz. And I'm going to choose a filter order of 2, and I call it my default filter. And I'm adding it to the list. Okay. So I'm selecting the filter now and include all the 8 channels again. And now the filter should be applied for all the 8 channels. You can see the shape changed again a bit. And I'm also going to cut the first 10 seconds of data because which can just be settling. So I'm removing the first 10,000 milliseconds, and then I'm taking the rest of the file. Now we can see that the signals look very flat because we also have to scale to a correct amplitude range. And EG is usually in between plus minus 50 or plus minus 100 microvolts. That's why I'm going to scale to plus minus 100 microvolts for all 8 channels now. And now we can already see eye blinks, EMG, and alpha activity in here. And we have preprocessed file for further processing. You can also do event-related potentials in GISs. You PBS Analyze, you can calculate classifiers. You can also apply Oscar in here. That's the Oscar Pro. So you have all kinds of tools for offline processing in PBS Analyze. Now we can also apply Oscar and check if he removes the artifacts nicely. It takes about a minute. And after a minute, we should see the result. We also have Oscar running in real time in g.tec. I think you've seen it in a previous talk from Francisco already. And after I've showed you how to process data offline, I'd also like to show you how to acquire data with G.Recorder and process it in real time in g.tec with a paradigm running in g.tec. That's something that might be interesting for research use cases where you're in a clinical environment and having G.Recorder recording data, but in parallel, you want to test some signal processing or some research experiment, then you can use this kind of setup. All right, Oscar is almost done. And then you can see again, it is changed and later on pretty clean. So Oscar removed a lot of artifacts nicely. Okay, for the next demo, as mentioned already, I'm going to open G.Recorder. Therefore, I'm opening the g.tec suite. I'm going to close the model that we've created now. Start a new model. Already open. So here's g.tec suite. And we're going to do the data acquisition within G.Recorder, and the signal processing will be done in Simulink again. In g.tec. Recorder is already opening. I've already connected to the Nautilus, and I have to configure the device again. We're going to add some hyperfilter again, so we can remove the DC. And then we can already get it logged in G.Recorder. We can already see eye blinks, clenching teeth, and alpha activity. So that looks good. In G recorder, you can additionally record it to HDF5, which is also a commonly used file format. You can do event-related potentials within G recorder. Basically, you can replay files. So basically, everything from visualizing EEG, preprocessing EEG, recording, and processing EPs can be done in recorder. And while this is running, I want to acquire the data stream in devices. And devising is our prototyping toolbox. So in here, we are more flexible in doing stuff. And first of all, I'm adding the remote data acquisition block in here. So we can acquire data from the recorder. And then I want to run a small paradigm in here as well. Therefore, I'm going to add paradigm presenter. I want to preprocess EEG again, and therefore I go to the preprocessing section. I'm going to add a cascading notch filter for 50 Hertz. I'm going to add a bandpass filter, so we remove offset and filter to a frequency range of 0.5 to 30 Hertz. Then I have 8 channels of EEG, and I want to add the trigger from paradigm presenter to the end. So on channel 9, I will have the trigger, while I will have on the other 8 channels. I'm going to add the group lead to the next one. And since we're running an event-related potential paradigm in this experiment, I want to trigger data. And therefore, I want to go to the signal manipulation and transformation section and add a trigger node in here. Trigger is, as mentioned, on channel 9. I want to look at a time window of 800 milliseconds, and we have a sampling rate of 250 Hertz. And the trigger value will be 1. So now we get triggered data. And with triggered data, we can visualize the event-related potential. And to visualize event-related potentials, we have to average a lot of them together. And therefore, I'm also adding the averaging block. And I'm connecting it to the trigger block because we are triggering at a certain time frame, and we want to visualize the triggered time frame. The final thing I'd like to add for this example is the vectors plot, because then we should be able to visualize the event-related potential as well. Therefore, I also go to devices, library, and visualization, and I'm going to add a vector scope. All right, it was a quick run how to set up an event-related potential pipeline. Maybe to sum it up shortly, we have the remote acquisition, which is acquiring data from the recorder. We have the paradigm presenter, which is presenting stimuli and triggers. We pre-process EEG and align it with the trigger. And we're triggering the data to actual timeframes, and we're averaging a lot of them together so we can actually see data. And I also want to visualize what the EEG, so I can be sure that the data is good. Therefore, I'm adding it to the filtered EEG output. All right, then we have to set up the device. The recorder is already running in the background. That's why it says the device is in use, but we can listen to the same device. have to quickly set up the model for 250 Hertz. So everything will run flawlessly. And I will open Paradigm Presenter because we want to make a visually low potential experiment. So we're having the EP paradigm right here. And I'm going to configure the EP scope correctly. You can also see the EPs arising. There is the configuration dialog. So we want to have a trigger offset at minus 100 milliseconds, and we have a sampling rate 250 Hertz. Now we can open the scope. So let's see if everything is running. We can see G recorder in the background. We can see the vector scope on the top right. We also want to see if we're receiving the same data in the HYSYS. That's what we have on the bottom right. And we have the stimulus presentation. Looks like everything is set up and running. And if I'm sitting still and looking at the screen, within some time, we should see EPs arriving. Yes, and looks like I'm already running out of time. You can see I just made it very quickly and just very little amount of tries, but you can see at around 300 milliseconds, some peaks are arising. And if you would use around 150 averages, you would have very clean P300 or your event-related potentials, similar to what you find in literature. All right. I hope I could give you an overview in the prototyping and real-time processing tools, as well as the offline processing tools of g.tec suite. And I'm ready to answer some questions.
Thank you very much for the nice presentation. Somebody's asking, can you use MATLAB 2023A or should it be B?
We tested everything with MATLAB 2023A. So it's the safest way to use that one, but in general, MATLAB tries to stay compatible with some limitations. So
Shalini wants to know which resources we have or which material they can get to train themselves. So maybe you can explain what we have on GitHub and YouTube and so on.
Yeah, for Unicorn, we have a lot of examples on our GitHub. So you find all the software manuals there. You also find some example data sets recorded with the Unicorn. So I recommend taking a look at that. And if you want to go more into research or higher sampling rates, higher amount of channels, I'd recommend to contact support and get some insights for the research amplifiers, or just take a look at the Spring School talks. Almost every amplifier will be there at some point.
And of course, we have many scientific papers. So for all the different experiments, you can find some scientific references, including hardware, software, experimental paradigm, the analysis that was done, signal processing. So we have more than 300 of them that you can use as a resource. And somebody's asking, what's the difference between Oscar Pro and the Oscar in Recorder and Simulink?
There have been some iterations. Basically, they should perform similar, but in details, I don't know if there's an Oscar talk, but I think some colleagues will present.
Actually, the difference is
differences.
very easy. Oscar Pro is the offline version, so when you have acquired the data beforehand, then you can use it in GBS Analyze. And the other Oscar is for real-time processing. While you are acquiring EEG data, it's already filtered. So it's a combination of very high oversampling, very steep anti-aliasing filtering and adaptive filtering. And this makes the output of the headset so clean so that you can easily use the data. Then Johannes is asking, do you have a Python or C API that you can funnel the data into using HiSys? So can you stream from Python into HiSys or the other way around?
Not by default, but we have lab streaming layer interfaces. So using that, it's very easy to stream data into some other framework.
So both g.HiSys is coming with LSL in the UDB interface, so you can just stream the data or also features that you're extracting to other applications. And this can be, of course, Python or a C# or a C API or any other language you want to use. It can also be an FPGA. And you can also do it the other way around. So in the Python API or in gpipe, we have also a communication interface, LSL and UDB, and then you can stream back to HiSys. This means you can use a Python library, and then you can plug it into real-time processing with Simulink to control, for example, an electrical stimulator in a closed-loop experiment. Then Kerti is asking, is it mandatory to learn MATLAB? Can we achieve this using Python?
If you have enough signal processing skills, you can create similar things in Python. If you're a researcher and you like this kind of drag and drop programming, then I'd recommend HiSys. There's no equivalent at the moment in Python available for PCI. So therefore, it's just an easy way without too much programming knowledge to prototype signal processing pipelines using Simulink and g.HiSys.
So in this HiSys professional toolbox, we have several hundreds of algorithms and Simulink models set up. So for your experiments, you will always, or most of the time, find a template for auditory stimulation, for example, visual P300, whatever you want to do, TMS experiments. Then you can either just start and stop and use these models, or you can also modify it. And this rapid prototyping environment allows you to very quickly set up a new experiment. So mostly we need a few hours instead of a couple of months or even years for implementing a new paradigm. And we can also help our users to do it together. And if our experts are on board, then we are talking of 2, 3, maybe 5 hours to set up a new experiment. So it's very fast and quick to test something out. And in Python, of course, you must be a programmer to know how to do. For modifying the Simulink models, you don't need to be a programmer. Is it HiSys or HIS? It's HiSys for high channel count system. And high-speed online processing. This was actually the original name, high-speed online processing. Then somebody is asking about the exam that's running in the almost last session on the last day. So it will be a multiple choice test with very general questions about BCI and neurotechnology. So it will not be g.tec or vendor specific. So we will not ask you for the name of g.HiSys, for example, but a question could be, what is event-related desynchronization, or how do you calculate event-related potentials? General EEG and ECOG knowledge. For example, what's the difference between EEG and ECOG? What are the advantages? What are the disadvantages? And it's picked from all the 140 hours during spring school. So be careful, but most of the questions are coming back several times. So you don't have to be shocked at the end, and it's multiple choice. But there's only one slot where you can do the exam, because we will provide all the questions to you. And then you get 30 minutes to fill it. You have to send back the filled exam to us. And then we provide to you the solution. So we will let you know the correct answers. Then of course it's over, because you cannot do the exam on the next day again. So reserve the time slot if you're interested in the exam. And with that, we actually answered all the questions. First time in Spring School so far that we were able to keep up. Thank you very much, Martin, for the nice presentation.